Okay, hello everybody. So today we are going to finish up our discussion in Chapter 5, Section 3. And in Chapter 5, Section 3, we have been introducing and working with properties of logarithms. So today what I want to do is give you an application problem where logarithms are used to solve a unknown. So it says one method of determining how the x and y values for a set of nonlinear data are related is to take the natural log of each of the x and y values. Now, let me give you some background really quick on this. Remember, back probably in Algebra 1, you had various times where you might have created a scatter plot of points in a graph, and then you drew a line through them. And then you found the equation of that line, and then you used that equation to model the data that you had collected. Well, not all data is linear. And so when the data is not linear, an approach to finding an equation that will represent that data well is to take the natural log of all of that data. It says if the points when graphed fall on a line, after you've taken the natural log of all your data, then you can determine that x and y values are related by the equation natural log of y equals m times the natural log of x, where m is the slope of the line. So m represents slope just like it always has before. So what this table shows is the mean distance from the sun, x, and then the period y, which is the time it takes the planet to orbit the sun, for each of the 6 planets that are closest to the sun. In the table, the mean distance is given in terms of astronomical units. And the astronomical unit is where the Earth's mean distance is defined as 1.0. So in other words, they're calling the distance from the sun to the earth 1 unit. And all of the other planets are measured by that standard measurement from the sun to the earth. And so it says find an equation that relates x and y. And so what you can see here is we have Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Now remember, the Earth, this mean distance right here, this 1, is the distance from the Earth to the sun. So what you see here is Venus is slightly closer to the sun than Earth is because it's only 0.7 units. And Mercury is a lot closer to the sun than the Earth is. Now, on the opposite end of that, you can see Mars is a little bit further away from the sun. It's 1.5 distance that we are from the sun. And then we get to Jupiter, which is more than 5 times away, and Saturn, which is 9.5 times further to the sun than the Earth is. So the period then is the time it takes the planet to orbit all the way around the sun. So you can see, remember, for us, the time that it takes us to go all the way around the sun is 1 year. So right here we have 1 year. Well, 1 year on Earth would actually be almost 2 years on Mars. It takes the seasons to go through on Mars. Jupiter, it would take 11, almost 12 of our years to go one full orbit around the sun. Saturn is even longer. It's almost 30 years to do one full orbit around the sun. So what we want to do is the first thing we should do is to take the natural log of every single one of these numbers here. Okay? Now, when we do that, you will get some new numbers, which I will show you in 1 second. Before I show you that, I want to show you a scatter plot of the numbers as they stand. So forget about the natural log. Just all the numbers that you see there are plotted on a coordinate plane, and you can see this. And remember, here, right here would be our sun. And so as you get further to the right, that is farther away from the sun. And as you go farther up, that is the longer amount of time that it takes to make one full orbit around the sun. So, as I said before, you would want to take this data is not linear. if you look at this data, you can see it's an exponential growth. It starts to go up like this. This is an exponential equation, not a linear equation. So we couldn't just use y equals mx plus b to represent this data. It wouldn't work because it's not linear. So what you can do is you can take each one of the numbers that you have for x and y and take the natural log of every single one. Now, when you do that, you end up with a new table. And this is the result of taking the natural log of every single one of those numbers from the first table. And you can see now we have all new points. But the idea here is that if you would take these and plot each one of these on a coordinate plane, you now get a linear graph. Okay? So the new points, after we took the natural log of each of the original points, gave us an actual linear graph that we can then solve the equation of much easier than you can for an exponential. And so what you see right here is the equation of that. Now I want to show you how to come up with that. So in order to come up with the slope, because remember our equation is the natural log of y is equal to m times the natural log of x. So what we need to do is we need to find that m. The way we find m is we find the slope. So the slope is y2 minus y1 over x2 minus x1. Now you can pick any of these to be your y2 and y1 and x2 and x1s. My advice would be to pick the 2 points that are the closest together because it's the easiest to figure out the slope. So I will call this x1 and y1, and I'm going to call this x2 and y2. So when I do y2 minus y1 over x2 minus x1, you can see I end up with 0.632 divided by 0.2421. Now, if I take my calculator and I go ahead and divide those two numbers, 0.632 divided by 0.421, you can see that we get 1.5. And if you go back down to here, they end up with the fraction 3/2, which is 1.5. So we were able to take the natural log of all of our data points, which gave us new data points. After we plotted those new data points, they formed a straight line for which we found the slope of that line. And once we have the slope, you can write the equation, which is what we have there. Natural log of y is equal to 3 over 2 natural log of x. Okay, that's what I have for you today. Now, this example is not exactly the same as the other examples that I would like you to try. These all involve using natural logs or logarithms, and they're going to be a little challenging. But as always, if you have any questions, you can email me, and I will do my best to help you out. Have a great day.